In this episode, we are going to cover transformers and look how we can use inductance, the concept of inductance and electromagnetism to change the output voltage from the primary to the secondary side of a transformer, so we can now have the ability to step a voltage up and use it, or step a voltage down and use it. Or sometimes we use transformers in a unity situation, or where you have a one-to-one and you have the same output as the input, but you're giving yourself some isolation. And we'll talk about all of that here shortly. So first concept we want to essentially revisit, since we've already talked about inductors, is inductive coupling. So we talked about how if you have two coils, if one of them is energized and you put another one in close proximity, if you put it in parallel, as opposed to perpendicular, you're going to have, if the windings are aligned, you're going to get better transference, and also if they're closer together as opposed to farther apart. Okay, so it says the magnetic field from one creates a voltage current in the other. Okay, so essentially, when you put this other coil in here, that magnetic field that's rotating around the first one will start to, just by the path of its flux, will start to store energy in that other coil. And when that happens, that generates flux of its own, and then that can generate a voltage and a current on the opposite side without actually physically touching the secondary of the second inductor over here. So you can actually transfer energy electromagnetically and have it be picked up on the second coil and then utilized to drive another load or do whatever. It says the most energy is transferred when the coils are coaxial, so that's where the windings align with each other, as opposed to this, and or wrapped around an iron core, which directs field lines down the center of the coils. So we're going to take a look at what that means here shortly. But let's just talk about the general form of a transformer that plays off this idea of mutual inductance. So an ideal transformer, it says a transformer in general raises or lowers an AC voltage. Okay, so in my intro, I said that we can step a voltage up or step it down. Specifically, I'm talking about AC voltage. It says, all you need is a pair of inductors, and it says it's nearly a short to DC signals, because, you want that changing AC signal, because it's going to generate a voltage on these, on this inductor here. Okay, so if you just have a DC signal hooked up to a coil like this, we know from our discussions previously that inductor is going to end up looking like a short once it gets to steady state. Whereas an AC signal is constantly changing, and then the inductor never gets to steady state. Okay, so difference in the symbolism here. This one does not have anything in the middle. This is an air core. These are just two coils that are in close proximity to one another with no medium to facilitate the electromagnetic energy transfer. Whereas here we've got an iron core, which, as it says here, it says in the previous example, it directs that magnetic field right down the center of the inductor. So let's take a quick look at a demonstration here. So this is from a website called Whisk Online that you may have heard of before. It's got a lot of computer science, engineering, math, science, that type of stuff on it. And it's HTTPS, and the website is www.wisc-online.com/learn. Okay, and there's a list of all kinds. It's not just engineering. So I just wanted to point out that I am using this site to do this. Okay. So, transformer, just two coils of wire in close proximity, preferably with their turns aligned. So the primary is what gets connected to the actual AC source, and the secondary is what we connect through this mutual inductance here, and we get a certain voltage out on the output. Now we can step it up, we can step it down. We'll talk about that shortly. It says when the AC power is applied to the primary, and here you see the sine wave, and you can see this graphic here is responding to the amplitude of this sine wave here. Okay, so you can see it's expanding as it grows, as it decreases, it collapses. Once it goes to the negative peak, Okay, so you can see as we're increasing the amplitude of the source, the magnetic field is increasing as well. And then it collapses as it starts to decrease. And then once it hits the 0 and starts to have a negative amplitude, it starts to increase again. And then when it starts decreasing back to 0, it collapses. So you can see, no matter if it's coming from the positive voltage or the negative voltage, when it starts to approach 0, the magnetic field is going to start collapsing. Okay, but this is essentially what's happening. It's happening very, very quickly because, essentially, if it's coming out of the wall, it's 60 hertz per second. So that means one of these cycles is happening every 16.7, essentially, milliseconds. So here we go. We've got another coil in close proximity. This circuit right here does not have its own power source. It's going to utilize the magnetic field here, and the flux linkage is going to be created in this coil. It's going to be picked up, and it's going to power this light. Okay, so this is what actually would be happening. This would be undetectable by the naked eye because it's happening at 60 hertz, presumably if this is plugged into a standard 120 volt RMS 60 hertz outlet that we have here in the United States. So here we go in slow motion. So there it is. It's being picked up by the secondary coil, and as it's collapsing, it's going in the opposite direction. So you're still getting an AC signal on this light bulb here. It's essentially charging and discharging this coil. So it says this electromagnetic transfer of electrical power from the primary to the secondary is called the transformer action. Okay. Now, again, we're watching this and, this is taking a couple seconds to make one full completion. So this is much, much slower than obviously what you would see in real life. This would be blinking so fast that you would not be able to detect it with the naked eye. It says, under normal conditions, alternating current occurs more quickly than this animation shows, and you can't see the light bulb flash on or off. I just said that. Instead, it remains illuminated as long as the light bulb's coil is close enough to be energized by the larger coil. Okay, so again, talking about the same motion here, so that it always, is powered by this other coil. It says a coil to which an AC power will be applied is shown. It will be used as the primary of a transformer. Okay, so all this is essentially a piece of coiled wire. That's all this is. All right, and it's wrapped in electrical tape, and you'll see what happens here. If you just want to look at this as the primary of a transformer, watch what happens next. It says a second coil. This time it's wrapped around, with this coil back here. It's wrapped around the outside of there's nothing in the middle here. It's just wrapped in a coil. Here, it's actually wound around this piece of plastic, and it's connected to this light bulb here. So the idea is that through that transformer action, while that first primary coil is plugged into the wall, it will transfer the electromagnetic energy to this coil. It will be picked up and powered by the light. And since it's internal, it's in close enough proximity that we should never see the light bulb go out. There we go. No physical connection, and the light bulb is energized. It says when the secondary coil is placed within the pulsating magnetic field formed around the primary coil, the electrical power is transferred, causing the light bulb to illuminate. And again, because it's within the magnetic field that's pulsating back and forth, and it's such close proximity, it appears as if the light bulb is plugged directly into the wall. Okay, so hopefully that helped you understand how this action works. So when we're talking about transformers, it says an AC supply signal is applied to the primary winding. Now, we always talk about the ideal component, whether we're talking about an ideal inductor or an ideal diode, whatever it is, right? So with an ideal transformer, we couple 100% of its energy and power and transfer it to the secondary. Okay, now that's not how it actually works. You know, there's some hysteresis loss, there's some winding loss, just a little bit, but it's not 100%. All right, we try to get it as close to 100% as possible, but you're always going to have these small little sources of energy drain in the transfer. Okay. So it says each turn in the primary winding induces the same voltage on a secondary winding turn. Okay, now obviously, like I said, that's not really how it happens. You can see the turns ratio there. That makes the mathematics and the calculations for the transformer circuits a lot simpler if we just assume that the turns ratio is equal to the primary to secondary ratio and then the secondary to primary currents. Okay, so here's a short video from MIT that kind of shows this mutual inductance, and not even in a transformer setting. They actually created an inductor radio where they had the output of the radio into a coil instead of a speaker, and then on the secondary side, so to speak, they have another coil of wire which is connected to a speaker. So the radio to the coil of wire on the primary, and then coil of wire connected to a speaker on the secondary. So there's no physical connection here, but they're going to be playing some music through this mutual inductance. So as I just alluded to, I talked about the transformer turns ratio. Okay, so it matters how many times the wire is coiled on the primary, and it also matters how many times the wire is coiled on the secondary. So the number of turns on the primary in ratio to the number of turns on the secondary is equal to the voltage on the primary to the voltage on the secondary. Okay, that's a direct correlation there. Now look what happens with the current, okay? Because, you know, in this case, if we had more turns on the secondary or if we had more turns on the primary, either one of those would be a one would be a step up situation where we're increasing the voltage from the primary to the secondary. Let's say, you know, we step it up by 2. We take it from 120 to 240, okay? You don't get something for nothing. So if you're going to increase, or let's say, just for easy mathematical purposes, let's say we double the voltage on the primary, you're going to have, I'm sorry, if we double the voltage on the secondary, you're going to get half of the current available on the secondary, okay? So it's an inverse relationship between the voltage and the turns ratio. So if you are stepping up the voltage, you will have less current on the secondary. If you are stepping down the voltage, you'll actually have more current on the secondary. So just to reiterate, transformer turns ratio, if we're talking about the secondary having more turns than the primary, that's a step up. If there are fewer turns on the secondary, that's a step down. If they have the same number of turns, we call that a unity transformer. And that's, again, one of those situations where you may just want some electrical isolation. You don't have a physical connection from the primary side to the secondary side. Okay, and so, you know, if you have a short or something on the primary, you should be okay on the secondary. And remember, the reason why is because an inductor, remember, it does not have an instantaneous change in current. So what happens when you have a short? The current goes through the roof, right? Essentially, especially if it's a, if you short everything out, if it's a complete short, you have massive, massive current. So that coil is going to take time to change from whatever current it was at to this new current it's being asked to, to jump to, and it's not going to be an instantaneous change on the secondary. So there's this common saying when you talk about the turns ratio, that the ratio of the voltages equals the ratio of the turns. Okay, you just have to remember that the turns and the voltages are directly proportional to one another, and that the currents, secondary and primary, are inversely proportional to the turns ratio. So you can manipulate those ratios and get, and try to figure out if you have the primary voltage, if you have the turns ratio, you should be able to figure out the secondary, or if you go in the reverse order, or if you have the primary and the secondary voltages, you should be able to figure out the turns ratio. So just a quick example with some easy numbers here. So here we have this laminated iron core. Okay, we've got the magnetic flux that's rotating easily now because we're giving it this nice ferromagnetic path to rotate in, and it goes right through the center of the coil. And so here we have a primary winding of 300 turns. We have a secondary winding of 150 turns. So going by what we just said, since the secondary winding has fewer turns, this is a step down transformer. And the ratio is 300 turns to 150 turns, which is a 2-to-1 ratio, primary to secondary. And it's always a good idea to note, sort of off to the side, what you mean by this ratio, because, if you just invert it, if you take it to the -1, it's a 1-to-2 ratio. So always note that typically we do this with primary to secondary. We say 10-to-1 or 12-to-1 or whatever it is. But it's always a good idea just to make sure that whoever's looking at it knows that you mean primary to secondary ratio. Okay, so if that's the case, we have half the voltage available on the output. And here we're saying on the primary we have 240 volts, which means half of that is going to give us 120 volts on the output. And here's another example. We're looking now at the secondary of a transformer over here. And we've got 12.6 volts available, and we've got 1 amp of current available. Okay, and so here we have V load equals 12.6, which would give us the 1 amp current through the load here, I2. Okay, so that would be 12.6 watts of power dissipation on the secondary. To find the turns ratio here, essentially we've got 12.6 volts on the secondary, which means if we have 120 volts on the primary, this would be 120 to 12.6. Okay, now 0.6 of a turn isn't really a good number, so you could go ahead and multiply these by 10 and say 1200 to 126. Okay, and then if you actually took that ratio and divided it by 2, you'd come up with 600 to 63. Okay, now you can further refine that and divide each one by 3, I suppose you could do. And so in which case you'd be down to 200 to 21. So I try to stick to whole numbers because I don't like partial turns in my ratio. But anyway, again, if you were to divide each one of these by 3, you would get 200 to 21. Okay, and I don't believe that you can take that ratio down any farther. I think this is a lowest common, or the lowest whole number value here. Okay, so it's roughly 200 turns to 21 turns to get you that 12.6 on the secondary. So the next thing we're going to talk about is what's labeled here as referred AC resistance or impedance. I've always heard the term as reflected resistance, so I will refer to this as reflected resistance. So it says the AC reflected primary resistance or impedance Z. Remember, Z is just the resistance of the circuit plus the reactance from the capacitors and the inductors. Okay, so that's just impedance Z. So the primary resistance or impedance Z of a transformer is the AC resistance seen by looking into the primary winding of a transformer. Okay, in other words, if you were to take the voltage at the primary divided by the current at the primary. Okay, and I say at the primary because if you model a source correctly, it should be a source in series with some resistor. Okay, if you're gonna model a source correctly with its Thevenin equivalent. Okay, so if you were to measure the voltage at the primary, not the source voltage, but the voltage at the primary windings and the current through the primary windings, if you take that voltage divided by that current, you will see the reflected resistance back on the primary. Okay, now this, you'll see in a second, has something to do with the load that's attached here. It says, now don't confuse this with the primary winding resistance, where, you know, if you were to disconnect the transformer and just take an ohm meter and measure the coil resistance, that's different. We're not talking about the winding, the physical windings, the resistance of those windings. We're talking about what's reflected back to the primary. So in the ideal load, we would have 100% transference from primary to secondary. No power will be lost in the windings, no hysteresis, and life is great, right? The turns ratio, you know, exactly calculates what we should expect on the output. So if we're going to accept the turns ratio as being, acceptable for our calculations, then we can also calculate the reflected resistance here back on the primary, right? And so we actually use that turns ratio in our calculation to make things simpler. So the reflected resistance back on the primary coil is the turns ratio squared times the value of the resistance of the load. Okay, so this is dependent on what this value is. Okay, because obviously if it's a higher resistor, it's gonna draw a different amount of current than if it's a lower value resistor. So what is reflected back on the primary that affects the operation of this entire transformer? So just as an easy illustration here, if we leave the secondary open, if we don't have a load attached here, then you don't have anything, we have the turns ratio times the load. The load is essentially an infinite resistance, which means you're going to have an infinite resistance on the primary, okay? So it says a secondary open is referred back to the primary or reflected back to the primary as an AC open. By the same token, if you were to short out the secondary and you essentially have 0 or milliohm resistance, you're only going to have 0 ohms or milliohm resistance on the primary, which is bad news because this can cause the transformer to explode. This is a very, very dangerous situation. Don't ever do this. So as I said, it's not possible to have 100%, 100% of the energy from the primary go to the secondary without any losses. And here are just a couple of them that I kind of hinted at earlier. Okay, so one of them is the copper loss. So the actual primary and secondary windings, you have just a little bit of power dissipation, because anytime you have a current through a resistor, you're going to have some heat offset, that you're going to have some power dissipation. So just by the nature of it being a physical conductor that's passing current through it, there's an inherent, it's very, very small, which is why, a lot of times it's negligible, but it's a very, very small loss, but it's still a loss. So you're not getting 100% from the primary to the secondary. Another problem is through the core loss. So we talked about how, having an iron core facilitates that electromagnetic flow right through the center of the inductor. When this happens, we get what are called eddy currents. So maybe you've been in a canoe before, or maybe a boat, and you've been floating down a river, or maybe you've been walking down a river or something like that, and you see these little, all of the water's moving generally in one direction, but then off to the side, you've got these little bitty swirls and what we call eddies. You get the same thing in electron travel through a wire, right? A lot of times, you get two things that typically happen. You can have an eddy current that can happen when you have these cores, but you can also have what's called the shear effect, where the electrons tend to travel on the outside of the wire no matter what size diameter the wire is. This has caused some manufacturing of wires to be hollow in the middle, since that's typically not used anyway when electrons travel from point A to point B. And then just by the magnetizing effects in the core, when those when you get that flux linkage in the core, You get this back and forth where it magnetizes, it demagnetizes. So it's charging and discharging, charging and discharging. So we call that that back and forth is kind of like a hysteresis. So you can actually calculate these losses and do a full, if you wanted to get a better, more accurate, secondary voltage, you would want to take into account all of these things, especially if you were designing one to manufacture it. You would know how much hysteresis loss there is, how much core loss there is, and how much you're losing in the windings, okay, to give better data to the person who's going to buy your transformer. So you can see here, these are used pretty much everywhere. On this laptop that I'm on right now, it's got a power supply that's plugged into the wall that's got a transformer inside it. Pretty much all devices, unless it's an AC motor, almost all devices in your home run off of DC, especially gadgets and things like that. So when you plug your wall wart into the wall, right, the big square or rectangle black box, or if you have an Apple product, it's a big flat white square. Those all have transformers inside of them. And so, typically you're stepping it down and then refining it into a DC signal from AC. And this goes all the way back to, power transmission a long time ago when we talked about AC initially, is that, it's easier and it's more efficient to transmit AC over long distances than it is DC, right? So it would be great if we all just had access to DC power, but we have to convert it from the AC into DC and then charge our devices, okay? So step commercial AC voltage down to low voltage. This is like 24-volt systems. If you've got a doorbell in your home or if you've got an irrigation system in your lawn, those typically run off 24-volt AC, and that requires obviously a step-down transformer to get it down to a workable voltage like that. So it says step commercial AC voltage down to rectified filtered DC voltage. That's a power supply. Anytime you plug a power supply into the wall, that's exactly what you're doing. It says step up line voltage to kilovolts for furnace or stove ignition spark. Okay, so typically the furnace and the stove run off 220, so it's already got a higher voltage input to begin with, and typically requires less current. But you do step that voltage up to kilovolts to get the thing to start. Okay, and here you see here, it says convert resistance. This is more of an impedance type situation, which you'll talk about more in your more advanced circuits classes, okay? And then the other thing, as I said earlier, sometimes, you just have a transformer that doesn't step up, it doesn't step down. You're just electrically isolating the primary from the secondary. And this is always a good idea if you have, like let's say you have a $10,000, $15,000 PLC setup. You're going to want to put some type of a unity transformer in there so that if you do have a problem on the primary, it doesn't zap your really nice, expensive automation equipment. So this gives us what I always say is the 30,000-foot view of how power gets to our homes and powers all of our devices. As you can see here, it says simplified view of the electrical distribution. A lot of people don't realize that the high voltage lines aren't just, thousands of volts. They are hundreds of thousands of volts. So, very, very high voltage lines can be, 138,000 kilovolts. There are some manufacturing facilities, like if you go to an aircraft engine manufacturer, a company springs to mind, sort of like Rolls-Royce or an Allison transmission type place. They have to have 100,000 volt service into their buildings to run the machines that make those big aircraft engines. So, obviously you have to talk to the power company to get that type of service into your house. Most residential is all 240, 120. But even before it gets to the local distribution transformer, it's still 12,500 volts, 12.5 kilovolts. So all homes, as far as I know, have 240 volt service. Now, you've got, obviously this last transformer here before it comes into your home, and you've got a neutral, and then most of the circuits in your home are tapped into one terminal, the 120 volts, and then the neutral. So most of the circuits in your home are 120 volts RMS. The only ones that are 240 like I said, are things like the stove, something, the dryer, and anything in your home that's got a 220 volt, 240 volt adapter to it is going to be using the outer terminals of this of these phases that are coming into your home. Okay, so an auto transformer says the auto transformer only has one winding. The primary and secondary share one terminal, and so you can adjust it. Variable transformers, if you wanted to, if you just didn't want a static transformer where the coils are what they are and you buy it at a certain ratio, there are ones that have a dial, almost like a big potentiometer, right? And so you can go up to 100 and 100% of what the primary voltage is. You can even go a little bit past. You can go down to like 10%. So you can determine what that secondary voltage is with an auto transformer. And so those are really handy, especially if you're in the lab and want to work with different AC voltages. If you're okay with 60 hertz, what comes out of the wall, then that's the nice, easy, quick way to get those different AC voltages. So if you have a transformer and you want to know if it works, the best way to test it is not to connect a load to the secondary, because if there's a problem, you don't want it to show itself when you plug it in. So leave the secondary open, don't connect any load to it, and then just put a light bulb or something in series on the primary. Okay, and it says first, obviously, disconnect from the circuit, then measure the primary and secondary winding resistance with an ohm meter. It says open circuit on either means that it's bad. So if it says overload, that's what most DMMs would say. It says the higher voltage side, typically a few dozen to a few hundred ohms. The lower side, typically a few ohms. Obviously, if that's a step-down transformer, which the majority of them are. Okay, so says if the lamp glows dimly or not at all, there's no short. If the lamp glows brightly, then there's a short and you've got an issue. But it's much better to check it this way than to hook up a load and plug it in and just cross your fingers. And so the final slide that I'm going to show here is just a very basic, about as basic as you can get, a DC converter circuit. Now, if you had a gadget that needed a very steady, very regulated DC signal, this isn't the circuit you may want to hook up to it if it has to be if it has tight tolerances. But if you just wanted to drive a load with a DC signal, believe it or not, it only takes a few components on the secondary of this transformer. So obviously we're stepping down. It doesn't say how much. It doesn't really matter. Well, I guess it matters that it has to be more than 6 volts, because otherwise the Zener diode will not pass current because it hasn't had the 6 volts applied yet. So let's just say it's a 10-to-1 and that we've got 12 volts on the secondary here. As we know with diodes, if we have an AC signal on this side and it's oriented in forward bias here, at least forward bias if you go from left to right with my cursor. So we're saying it's in forward bias here. On the positive hump of the sine wave, the current will pass through the diode, okay? It'll get stored on the capacitor, and this 6-volt Zener diode will regulate that this is only going to store 6 volts, okay? And that way you get a nice, or a fairly regulated 6-volt output, okay? So you might be saying, well, what happens on the negative half of the cycle? Well, the current is going to try to be pulling in the other direction, and this diode is going to be in reverse bias at that point, and it will block it. So this is what we call a half-wave rectified signal, because you send an AC signal through a single diode, it's only going to pass through the positive humps, and then it's going to be 0 for the negative, and then it'll go positive again. So this circuit is only going to get positive voltage, and the current is only going to flow in one direction. Okay, now if this happens quick enough, you can keep this capacitor charged and get a fairly steady DC out. Okay. It's not 100%, but it is a fairly regulated. You're still going to get some ripple voltage on the output here. You would want to do some more circuitry, in another more advanced circuits course where you talk about electrical components. There are other electrical components you can put in here, along with a full wave bridge rectifier, which takes 4 diodes, and instead of just blocking the negative half, you would actually turn the negative into a positive. And so now you've got positive hump, positive hump, positive hump. Add some, some other massaging circuitry in there like capacitors to reduce that ripple from when it goes from hump down to 0 back up to the peak down to 0. You would just go, if you're following my cursor, you would just go to here, and then before it goes all the way down to 0, it's already being charged to the next one. So you get more of a what looks like waves on an ocean, as opposed to just humps that go to 0 and then another hump that goes to 0. So you refine that transition from peak to peak until you get to the point where the peak to peak transition just looks like a flat DC signal. Okay, so that's always the goal when you do a power supply, is that you're trying to reduce that ripple voltage on the output by, adding some other circuit components in here that give you a more flat, more reasonable, constant DC signal. Okay. Okay, now what I want to do is a couple of examples on the board with this reflected resistance, because you're going to be asked to do this on quizzes and the exam. Okay, so now we're going to go ahead and do one of these problems with the reflected resistance. So as you can see here, I just have a simple AC source, 108 volts RMS, 1 kilohertz frequency. Frequency doesn't really matter for this type of problem, but I have the reflected resistance equation for back here on the primary. And again, that is all based on what the load is and also what the turns ratio is. So you square the turns ratio, multiply times the load. Okay. So in this case, our turns ratio is 3 to 1. So we take that times the 4K ohm, which is 9 times 4K ohm, which gives us 36 kilo ohms. Okay, so for this type of problem, I want to know the following. I want to know what I primary is. I want to know what I secondary is. And I want to know what the voltage on the secondary is. And then I want to look at what is the power, the voltage times the current over here. Does that equal the voltage times the current over here? Okay, so I want to look at the power out and see, does it equal power in? Okay, so here we go. First thing I'm going to do is I can go ahead and find the primary current if I would like, or, well, yeah, I think that's what I'm going to do. So I've got my 36 kilo ohms that I'm seeing here reflected back onto the primary windings. Again, this is not the resistance measurement of these windings. This is simply the, based on the load, based on the terms, what's reflected back onto the primary that will essentially help set what this primary current is. Okay. So here I'm going to go ahead and calculate I primary, and that's going to be the voltage on the primary there, that 108 volts RMS, divided by the reflected resistance. There's no other series resistance here, so I just have this, divided by 36K. And that gives me 3 milliamps. Okay. Now we know from the turns ratio that it's 3 to 1. Okay. And so when we have the turns ratio on one side of the equation, if you're talking about current, it flips. Okay. So if this is 3 to 1, this is stepping the voltage down, which means it should be increasing the current. So this is going to be, as far as I secondary goes, it's going to be 3 times this current. So we should have 9 milliamps on the secondary here. Okay. All right, so let me go ahead and write this. Let's do this in green. So we've got I primary as 3 milliamps, and we've got I secondary as 9 milliamps. Okay. All right, so let me go ahead and erase these. Okay. So since we have both the currents, we can go ahead and find out what Vs is, and we can do that one of two ways. We can take, since it's 3 to 1, we can take 108 and divide that by 3, okay? And that'll give us what? 36 volts. The other way we can do it is take the 9 milliamps of current times the 4 kiloohms of resistance and come up with the same thing, okay? So on the secondary here, we've got 36 volts, and that's RMS, obviously. The currents would be in RMS as well, okay? So that's a simple example. If you just treat this as a perfect ideal source that has no series resistance, then this is the easiest way to do this problem, okay? So let's go ahead and add some resistance on the primary and see how that affects the calculation here. Before we do that, I said I was going to look at the power out and the power in. So here's the calculation for these. So we calculated that we had 3 milliamps of current on the primary, 108 volts on the primary. We also said we had 9 milliamps of current on the secondary and only 36 volts on the secondary. So if we do our simple P equals V times I, there's 324 milliwatts on the primary. Power out, 9 milliamps times 36 volts. That also equals 324 milliwatts. So again, this is assuming an ideal transformer and that the turns ratio times the load is the reflected resistance back. And, you know, we make these calculations nice and tidy, okay? Obviously, you're going to have some loss from the input to the output. We don't have perfect systems. Okay. So here's the next one, and as you can see here, I've just gone ahead and added another resistor, and everything else is the same from the previous example, okay? So here we've got 18 kilo ohm in series here, okay? Better replicate, I don't know, you know, just choosing a number that makes all this math work out nicely, but anyway, put a series resistance in here, okay? So that means, you know, the current is going to change, okay? You can see that the reflected resistance, I've already done the calculation here, but it's the same because it's all based on the turns ratio and the load. It has nothing to do with this resistance on the input over here, okay? So the difference is when I go to find the primary current, okay, I have 108 volts still, but now I have to do this resistance plus this resistance because this is a little series circuit here, okay? So I've got in the denominator 18K plus 36K. So I have 108 volts divided by 54K. Now you can see why that value was chosen, so that makes this nice and easy. Now we're at 2 milliamps available on the primary. Did it in green last time, didn't we? So this is 2 milliamps. And then over here on the secondary, again, this is a 3 to 1. So we are going to increase the current. So the current on the secondary is found with taking the 2 milliamps times 3. And so we have 6 milliamps on the secondary. Okay. Now, as far as calculating the voltage on the secondary, okay, we can no longer just assume that this is 108 volts on the primary because there's some voltage drop across here, okay? So in this case, I'm actually going to calculate the voltage on the secondary and then figure out what the voltage on the primary is from that calculation. So voltage on the secondary is 6 milliamps times that 4 kiloohms. And I only have 24 volts on the secondary. Okay, so that means the voltage on the primary, and again, I'm talking about, you know, from this terminal to this terminal, okay, this is past the 18 kilo ohms. So there's 108 volts here, but there's not 108 volts here because we have, you know, by definition, we have to have a voltage drop across this, okay? So we only have 24 volts on the secondary. So when we multiply it to go the other way, we take 3 times the 24 volts. And that gives us what, 72 volts on the primary. Okay. All right. So again, you know, the primary current is calculated by taking the total voltage here divided by the total resistance. And if you want the actual primary voltage that's available, you would have to subtract this from this, okay? So it looks like it's, what, 36? 2 milliamps times 18 kilo ohms would be a 36 volt drop. I don't have any colors left. Plus 36 volt. Boy, that's horrible. 36 volt drop across there, which means we have left 72 volts. Okay. All right. Well, hopefully this helps. And good luck on the quiz and on the exam.